Let's talk about the devices we use every single day. Because inside our sleek, silent gadgets, there's this chaotic, high-speed battle being waged against the fundamental laws of physics.
It's a conflict you can't see or hear, but trust me, without engineers fighting on the front lines, none of our modern technology would be reliable or even possible. So what exactly is this war?
It's a war against the very nature of electricity and heat, all crammed into these impossibly tiny spaces. And you guessed it, every single circuit board is the battlefield.
All right, let's get into it. To really understand this fight, you first have to understand the terrain. We're talking about the printed circuit boards, or PCBs, that are the foundation of pretty much all electronics.
Just try to picture this. Billions of signals, each one a little piece of data, just racing through these microscopic highways. At these speeds and at this tiny scale, things are bound to get messy. The signals, they don't always stay in their lane. And that brings us to our first invisible enemy, crosstalk. So what is it? It's basically the unwanted coupling between those signal traces. It's electricity just not staying where it's supposed to.
Yeah, when one signal's energy kind of jumps over to a neighboring trace, it just garbles the data. It's like electronic eavesdropping. And this can cause glitches, it can slow down performance, or, cause an outright failure.
Okay, so the next big challenge is just keeping the power stable. Think about it. When millions of transistors switch on and off at the same time, it creates this huge, sudden demand for current. This causes the voltage on the power and ground lines to fluctuate. They call this effect bounce.
And these tiny little groundouts can starve components of the stable power they desperately need, which leads to crashes and all sorts of unpredictable behavior. I mean, your processor can't exactly think straight if its lights are constantly flickering, right?
Oh, and the list just keeps going. Engineers also have to fight resonance, where the board itself starts to hum electrically, kind of like a wine glass at just the wrong frequency. Then you've got impedance mismatches that act like roadblocks, bouncing signals right back where they came from. And, of course, electromagnetic interference, EMI, where the device basically becomes an unintentional radio station, messing with all the other gadgets around it.
So, okay, with this whole army of invisible enemies, how in the world do engineers even begin to fight back? I mean, they can't just build a board and cross their fingers, right? That would be ridiculously expensive and take forever. No, they need a way to see the future. It really comes down to this. You can't fix what you can't see. This entire war has to be fought and won in the digital world, way back in the design phase. They need a crystal ball that can show them exactly where all these invisible problems are going to pop up. And that crystal ball? It's a piece of software called Ansys SI Wave. Think of it like a virtual X-ray for electronics. It's a simulation tool that lets engineers see how electricity and heat will behave on their circuit board designs, predicting crosstalk, power bounce, and EMI with really incredible accuracy.
So, you might be wondering, how does this actually work? How can a piece of software tame the laws of physics? Well, let's break down the whole workflow into 3 simple steps. First up, the engineer imports the digital blueprint of their circuit board. Simple enough. Next, SI Wave's super powerful physics solvers get to work, running all these complex calculations to simulate everything from voltage drops to those weird resonant frequencies. And finally, and this is the cool part, it spits out the results as these visual heat maps and plots. It's basically highlighting every potential problem area in bright red.
Okay, now what's really interesting is how these abstract simulations translate directly into the reliable performance we all just expect. Let's take a look at how this virtual process actually builds the gadgets we depend on every single day.
So for example, when SI Wave runs a DC IR drop simulation, it's checking for that power bounce we talked about. And the result? Your laptop gets stable power and doesn't crash when you're in the middle of something important. Or when it runs a crosstalk scan, it's hunting for those interfering signals. The benefit for you? Your Wi-Fi is fast and your calls are crystal clear. It can even co-simulate with tools like IcePack for thermal analysis to make sure your phone doesn't get too hot to handle. See, it's a direct line from simulation to the real world.
Now, using a powerful simulation tool like this, especially in a world so concerned about data privacy, definitely raises an important question. What kind of information is being shared when engineers are fighting these battles in the digital realm?
Well, the Ansys Product Improvement Program is designed from the ground up to be completely anonymous. It focuses on how the software itself is performing. Things like which features are being used and on what kind of hardware, all so they can make the product better.
But, and this is crucial, it never collects personal info, it doesn't collect company names, and most importantly, it never ever touches the intellectual property of the design itself.
So that seamless performance you get from your phone, your car's electronics, your computer, it's not an accident, it's not magic. It's the result of engineers fighting and winning thousands of these tiny, invisible battles in simulation, long before that device ever reaches your hands.
And that leaves us with a pretty fascinating question for the future, doesn't it? As we keep pushing technology to its absolute limits, shrinking components, boosting speeds even further, the laws of physics aren't going to change. The battlefield is just going to get smaller, and the enemies are going to get tougher. So what new invisible battles are waiting for engineers just over the horizon?